Okay, so we are going to continue with section 1.4 using the Moivre's theorem to find trig identities that are of type trig function to the power of n theta. Well, that trig function is going to be usually sine to a power or cos to the power, occasionally tan to a power as well. So the useful identities for this part are, so z plus z to the power minus 1 is equal to 2 cos theta, and obviously a more general form, z to the power of n plus z to the power of minus n is equal to 2 cos n theta. The second one is with a minus, so z minus z to the power of minus 1. This gives you 2i sine theta, and z to the power of n minus z to the power of minus n, that gives you 2i sine n theta. Now you have already derived this identity, z plus z to the power of minus 1 is equal to 2 cos theta in one of the examples before, and z minus z to the power of minus 1 equals 2i sine theta. You also had to do that in one of the questions in exercise 1a or 1b. One might have been 1c, can't remember. Anyway, what I will do though, I'll just derive this identity for you, so you've got an example of what how you could do it. So let's imagine you've been asked to prove this identity. Then you're going to, if you want to treat it as a proof, you want to start with one side and then arrive at the other side without rearranging. So we're going to start with the left hand side. Okay, so in those questions we are going to use z as our complex number with modulus equal to 1 and argument equal to theta. So you can write it in trigonometric form like so. So if z is equal to cos theta plus I sine theta, then obviously z to the power of n is going to be cos theta plus I sine theta to the power of n. So this is simply cos n theta plus I sine n theta. So we substitute here straight away cos n theta, add I sine n theta. Now regarding z to the power of minus n, if you bring it to the take it to the power, raise it to the power of minus n, we are going to have cos minus n theta plus I sine minus n theta. And obviously what you can do is, this is clearly complex conjugate, just take that minus in front of sine, as sine is an odd function while cos is an even function, so it's going to be the same whether cos theta, n theta or cos minus theta are equal. Okay, so let's carry on substituting. We are going to add to this cos n theta and then minus I sine n theta. I've added it when it says clearly taking away. I did think we were getting, there you go. Okay, so let's subtract. We are going to get cos n theta minus cos n theta, so these will be cancelled, and you'll be left with I sine n theta minus negative I sine n theta, so it's clearly going to go to a plus. So we've got 2I sine n theta, which is the right hand side, so it's proven. Okay, you should be able to derive any of these four identities at any point. Quite often it's asked in part A of a question on de Moivre's theorem. So we're going to go ahead and use those identities to answer a question of the second type. So here we could see clearly you've got cos to the power 5 theta, and we've got to find the values of a, b and c on the right hand side. So as it's cos theta, that invites you clearly to use the identity involving cos theta. So it's z plus z to the power minus 1 is equal to 2 cos theta. I'm going to quickly rearrange this identity, because if this is true, then cos theta must also be equal to a half z plus z to the power minus 1. So we are interested in finding cos theta to the power 5, so we are going to raise both sides to the power of 5. So cos to the power 5 theta must be equal to, if you raise this side to the power of 5, you get 1 over 32, and it's z plus z to the power of minus 1 raised to the power of 5. So we are going to use binomial expansion, so it's, let's just quickly generate the numbers using Pascal triangle. There you go. So the coefficients are 1, 5, 10, 10, 5, 1. I'm actually going to, should be able to squeeze it all in to that line. So let's expand this expression. So it's 1 over 32. Don't forget that this 1 over 32, quite often when you have to do something for a long time, students forget to write the multiplier in front of the expansion. Okay, so the first term is raised to the power 5. Then you've got 5z to the power of 4, and then you've got 1 of z to the power minus 1. Plus here we're going to have 10z to the power of 3. And then z to the power of minus 1 squared is clearly going to give you z to the power of minus 2, because you're going to multiply the powers. So straight away could write z to the power of minus 2. The next one is going to be 10z squared, and similarly you've got z to the power of minus 1 cubed is going to give you z to the power of minus 3, plus 5z, and then you've got z to the power of minus 1 raised to the power of 4, that gives you minus 4, and then finally you've got z to the power of minus 5. Okay, so now we're going to just tidy up those terms, simplifying them. So 4 add minus 1 gives me 3, so you've got 5 to the power of 5z to the power of 3. Here you've got 10z to the power of 1, then you've got 10z to the power of minus 1, and then you've got 5z to the power of minus 3, and then the last term stays as z to the power of minus 5. So now the next step is to pair the terms that kind of like each other, that are very similar to each other, together. So you can see that z to the power of 5 nicely goes together with z to the power of minus 5. So not only you have one of those, but obviously the powers are the same in terms of their magnitude. So one is 5, and then magnitude of minus 5 is also 5. So then 5z cubed has got a brother of 5z to the power of minus 3. So you've got 5 lots of this pair. Okay, and then last one, you've got 10 lots of z that goes nicely together with z to the power of minus 1. Okay, and now you should notice that, why did I pair them up? Because each pair here can be replaced with a trig function. So this time you could, the two are added together. So we're going to use our identity z to the power of n plus z to the power of minus n, because there's a plus in each pair, is equal to 2 cos n theta. So let's do that. We're going to use this one. It's always a good idea to state the result that we are using in a question like that. So here we're going to replace it with 2 cos 5 theta. Now, if I mentioned to you the most common mistakes students make, they don't forget to put 2 over here when it's only one of them, but when it's 5 or 10, they very often forget to put 5 times 2 cos 3 theta, and therefore their values of A, B, well, A might be correct, but B and C will be incorrect. Here we've got 10 times 2 cos theta. So the last step is multiply each term in the bracket by 1 over 32 and tidy it up. So 2 over 32 is 1/16 cos 5 theta. This one, 5 times 2 over 32, so 2 will cancel, you're left with 5 over 16 cos 3 theta. And here we've got 10 times 2 over 32, so 2 cancels, 10 over 16 cancel by 2. You're going to get 5 over 8 cos theta. So the values are A is equal to 1 over 16, B is equal to 5 over 16, and C is equal to 5 over 8. There you go. So this takes us to the end of example 11.